Hello, in this lecture tour, as you may be aware that last time we were looking at the basic comparison between a microprocessor and a microcontroller, and we did take some time to try to make you understand what we are looking at, and I hope that things were clear. Now, I'd like to pick up from where I ended to try to make you understand now further in this lecture too. Now, if we try to look at, the basic outline of what we're going to look at is what you see right here, as you can see, and this is what we're going to look at today. Now, the basic principle of operation, microprocessor and memory, and the memory structure, the bus lines, types of memory, the behavioral architecture, memory layout. So here we are now trying to hit the nail on its head on what exactly we're going to focus on in this course. So because we're going to be dealing with the AVR architecture, we're going to deal with the Atmega 32 microcontroller, and we're trying to go into details as well on those things. Now, right now, let's try to look at the microprocessor, microcontrollers, and memory, right? So now, guys, at the most primitive level, that is at the most primitive level, a computer, if we talk about a microcomputer, like we said, a microcontroller is a microcomputer, it consists of a microprocessor. Now, the microprocessor, which is the CPU, which executes the instructions, and we know that we have also memory at the most primitive level for storing instructions as well as other data. Now, we'll have a detailed discussion on the memory because we have two types of memory, especially when we deal with the programming. We have the memory where we store the program or the code, and we have the memory where we store data. All right, so there's memory for storing the code and there's memory for storing the data. But of course, we have got all these different types of memories. Some of them could be that you can only store volatile information. Some of them you can store permanent information. But in terms of which memory to store what, and depends on whether that memory is for storing the code, the instructions that you write, or it's a memory where you just store data. All right, now data, this is the data on which the instructions are going to work on. All right, but we're saying that at the most primitive level, a computer or a microcomputer or a microcontroller in this case should contain the microprocessor and the memory. Okay, so the processor for executing the instructions and the memory for storing data or for storing the code. Right. Choose to make some progress. Just put it in view screen mode. Now let's just try to discuss a little bit the microprocessor and the memory unit. Now, as you can see here, there is a microprocessor here, and by now it is clear to all of us that it is actually clear to all of us that if this is the microprocessor and there's a memory unit, then there is what we call in this case, I'm giving an example, is an address bus. Now, the function of the address bus has already been mentioned. Now, we did mention that the address bus is actually those links that link the CPU or the processor to the memory unit, and the function is to actually locate the address of a particular cell. Now, because you realize that the memory is going to be divided, it's actually divided into cells. For example, guys, I'm explaining these things ahead so that when you meet them, you actually will see what I'm talking about. So if this is a memory location, what normally happens is that this memory unit, no matter how big it is divided into chunks, pieces of memory, right? Now, this chunks piece of memory, there is a way in which we need to address them, or there's a way in which we give them the index values. Now, index values in this case are referred to the addresses, in other words, because for example, if this is an index value number 0, this is number 1, this is number 2, this is number 3, this is number 4, this is number 5, 6, and 7. So this whole memory has been divided into these cells: cell number 0, cell number 2, cell number 3, cell number up to cell number 7. You understand, right? Now, how do I address this cell? Right, cell number 0. Now, cell number 0 here, actually, it's going to be addressed by the address bus. So the address bus will carry the particular cell. Suppose that this is a cell that we need to work with, and there's some sort of data. Let's say data is 10010 because it's binary. Right? So the function of the address bus is to actually locate what particular cell or memory location are we actually dealing with. Right? Are we dealing with this particular cell? Is it the place where we want to store data, or that we want to retrieve information? Suppose that that data is this one that is there, and data can, in this case, what we mean by data, we just mean binary numbers. Okay, so now it could be this cell as a reference, and so these addresses we're talking about, they are actually literary numbers, and they are indexes that help us locate a particular location in memory. And what helps us to do that is actually the address buses. And as you can see here, we're saying that this is an address bus of 15 bits. Now, if we're saying that it's an address bus of 15 bits, so you can see here, guys, that it's written A0 to A15. So A0 to something like A15. A15 is just because they are in fact, are A0 to A14 actually, right? So there are 15 buses, but we start the index from 0. Now I want to mention here that when you see an address bus that is used to refer to which particular cell in memory for doing that, there are, from the address bus, we can tell how many locations are actually possible in terms of the index values, or in terms of the addresses that we can give. Now, the index values are the addresses, but I want to mention here ahead of time that you will actually see that these addresses, you will see that they'll be written in hexadecimal, right? Now, I want to mention here, for example, the way I've written them, I've written them in decimal, but usually, on a computer system, you may see them written as hexadecimal. Sometimes the hexadecimal, for example, for address number 0, you will see it written as 0 times 0, maybe 0 or 0 something, or just zeros like that. What just simply means this is the hexadecimal equivalent, and we're putting a times. The times shouldn't really matter that much because some controllers will express these times, but what matters is really the number after the 0 here. So this is maybe could be hexadecimal, and then this you could have also like 0, 0, 0, maybe 1. That just tells you that this is address number 0, for example, number 1, for example, and things like that. And sometimes the cells themselves, which is the memory cells, could have a dollar. They could be preceded by a dollar sign, like 0, 0, 0. There could be 4 zeros. Now that indicates the memory cell location, but expressed in hexadecimal. And usually the cell locations are actually expressed in hexadecimal. I'm written them like this in decimal, but you'll see very soon that when we start demonstrating these cells that are found in memory, they will be addressed. Their locations will be in terms of the hexadecimal, and you should be comfortable to do that, and you should be comfortable with that. Now, this dollar sign, some microcontrollers may choose to be a bit unique in how they handle. They would want to precede their cell addresses with a dollar symbol, but that's not a big deal, because even if it's expressed with a dollar symbol, but what matters is the number that comes afterwards. And this actually shows you that this is a hexadecimal value, but then it's holding 4 decimal places. It's holding 4 places, meaning that that cell location will be represented in terms of 4 digits. right? So cell 0 will be 0, 0, 0, 0. Maybe cell 1 will be 0, 0, maybe 0, 1. But if you change that to hexadecimal, maybe it's 0, 1, 0, or 0, 1, something. So you actually see all of this come to play. I just want to make you prepare your mind in advance. But right now, you can see here that we have the data buses. Now, okay, so coming back to the same, I did mention that the address bus actually may also define for us the number of cells that are possible with that. And the number of cells that are possible, knowing just the address bus, is actually, we can give it to the 2 to the power 15, right? Now, 2 to the power 15 actually means that these are the numbers of the cells that are available, that are possible, that we can come up with the cell locations, and that also refers to the size of the address bus. Okay, sorry, that refers to the size of the memory size. So the memory size will be 2 to the power 15. All right, 2 to the power 15 what? 2 to the power 15 bytes, right? Because the cell packing will mention very soon that cell packing can be in bytes or 2 bytes. But just right now, just understand, right? There's something to the 2 to the power 15, which will define the memory size. But also we have the data bus, right? The data buses are actually 8-bit long. And in this case, of course, we have the 8-bit data buses. There could be actually more, but this is just an example. Right, and then we mentioned what the data buses are used for, and these data buses, they're actually used for carrying data. Now, the enable and the read-write control. So this enable could be just an extra line that, of course, we understand. If we do have different memory units, then definitely there must be some sort of control lines. Okay, these control lines. You can even say that these two may belong to the control unit, control bus, because now we have to enable the chip or the memory under discussion, or the memory that could be worked with. It could be the ROM, the EEPROM, or it could be the SRAM, or other types of memory locations. We need to enable a particular memory unit for that unit to be worked with at a particular time by the microprocessor. And then we have got the read-write control line. Are we reading? Are we writing? So that could also be something that is needed as well. Now, let's try to look at the memory structure for a short while. Now, if you look at the memory structure could be what we see right here, just like I was explaining, that each memory, the memory is divided into cell. You can see this is cell size, and then we have got also the address. This is a section for the address. And what you see here is the hexadecimal equivalent of the particular cell location and what it is actually found at. Now, for example, we've got this is 0 times 0, 0. These are the main ones that you need to concentrate on to try to tell that these are hexadecimal values that we try to adopt. And this particular address, for example, represent the cell number 0 in this case. Now, the thing is, if we say this is the address and this is the cell, now a very interesting thing that comes up now in memory locations or in cell memory locations is actually the concept of what are we exactly dealing with. All right, are we talking about the cell locations in terms of the size, right? How long are the cells, or what is the amount of data can the cell hold? That becomes very critical in memory sizes as well. Now, when we talk about the cell itself, the amount of information that it can hold, in this case, we can say that the cell can either be a byte long or 2 bytes long, right? 2 bytes long, that's the cell size. Now, in terms of the simple terms, a byte is actually 8 bits, or 2 bytes is actually 16 bits. So meaning that a cell can hold up to about, now here decision is made, how many bytes can the cell hold? the cell could hold up to 8 bits, or the cell could actually hold up to maybe 16 bits. So depending on the number of bits the cell holds, that becomes the size of a cell. And in this case, we're saying that this cell in this case can hold either byte or 2 bytes. A byte, 2 bytes are also called a word. In other words, 16 bits are also referred to as how many bits? 16 bits are also referred to as 2 bytes. And a byte is also just like as a word as 1 byte, just the way it is. Okay. Now, we just want to try to see if we can briefly also analyze these two. So these are the cell sizes, and the cell size is actually determined by how many bytes it can hold or how many bits it can hold. All right. So in this case, so 1 byte is 8 bits and 2 bytes 16 bits, which is also called a word. Right. But the memory, so based on the cell size, we can actually determine the size of the whole memory structure. So for example, with memory size is actually given as the number of cells, the number of cells that there are, how many of these cells, times the cell size. All right. Now the cell size can be, like in this case, a byte or 2 bytes. All right. So now if times the number of cells. Now units in which memory is measured is bytes. The units in which the memory is measured is actually bytes. But when we have 1024 bytes, 1024 bytes, meaning that that's the unit of measurement. We're saying it's a byte. It can hold 8 bits at the minimum. But if we have 1024 bytes, then that is referred to a 1 kilobyte memory unit. And if we have 1024 kilobyte, now here we have, now if we have 10 and 1024 bytes, 1024 bytes, then that refers to a 1 kilobyte. And if we have 1024 kilobyte, which is 1024 of this, then we have 1 megabyte. And if we have 1024 megabyte, we have 1 gigabyte. If we have 1024 gigabytes, then we have what? 1 terabyte. Now, 2 operations with memory. So there are, since this is the memory structure, there are basically 2 operations we can carry out with the memory. What are these 2 operations that we need to work with when we deal with memory? 2 operations we can deal with. So the basic things, guys, that are very important for us to really appreciate and understand is that we can do 2 operations with memory, right? What are these 2 operations we can do, right? We can also, what is it that we can do with the memory unit? We can actually write to the memory location, right? So we can write to a memory location. And what can we write to the memory location, and how do we do it? So the first thing we need to do is to specify which cell, which memory cell. Are you dealing with cell number 0? And if that is the cell, so the first thing is that we identify what the cell is that we're dealing with, we're trying to deal with. And the second thing is we need to specify the value, right? What value are we trying to write to that particular memory location? So for example, you can have 001, which is an hexadecimal. That is the cell location. So if you want to write something, then you need to specify the address. So I can specify the address like 0 times 01, and I'm trying to write value, what value it is. Sometimes they say I write CB. Now CB, I've written this value in hexadecimal, or it could be CA. I've written this value in hexadecimal, but then the data is taken as a binary number. Now, binary numbers are the way computers would process data, but we would want to sort of put the value in hexadecimal just to kind of shorten the whole process so that it becomes easy to read. All right? So that's really the issue here. So we can do the write operation. Write operation, and we can also do, what kind of other operation can we do? we can also do the operation. We can do the read operation, for example. All right, so here we can also try to read. Now, what is it that we're doing in terms of the reading? So we are actually reading from the cell itself, from these cells which are found in memory locations. What do? We could actually read. And how do we read? So in reading, we specify the address from where we're going to read. We specify that address, and also we return a value that we're going to read. So now this is the job of the if, let's say for example we are writing, this is the job of the address bus, right? So because the address bus would actually first of all, because remember there is a CPU, and there's a memory, right, location. Now, and this memory is divided into cells. But then now, if the CPU wants to write to a particular memory unit, then through the usage of the address bus will actually locate the particular memory cell. And that particular memory cell would be written with data, right? That's what happens. And then now, if we want to read from the memory unit, again, the address bus will, again, the specific address should be located from that memory cell so that data is read from it and taken through the data bus to the microprocessor. Now, let's just look at how do we store data in memory, right? So, for example, how do we store data in memory? So, for example, how do we store a 1 byte at a particular location, for example, right? Now, here are all the cell locations in hexadecimal, and here the cell size is actually 1 byte. 1 byte means the size of this cell is actually 8 bits, right? And at cell location number 0, let's say we want to store 1 byte. Now, how do I know it's 1 byte? Well, if I count the bits, there are 1, 2, 3, 4, 5, 6, 7, 8 bits. And I have to store these 8 bits, which is 1 byte, to a stored address this. Now, the first thing I'll do is to change these bits into hexadecimal. Now, why am I doing that? Well, because in hexadecimal, it will be less messy, it will be more readable to store in hexadecimal. But then the data, of course, is actually stored in binary, but we change to hex so that it's easy for us as humans to actually read than to have all bunches of zeros and ones, which could actually fry our eyes, right? So now here's the point. Here's the point. So I'm storing this to this. So I change that to hexadecimal. And at this address, I'm storing the CB. CB will be actually stored at that address memory location. All right. Now here's another question. How do I store 2 bytes at a particular location? Let's say through this. Now we have, though the cell size is 1 byte, but I have data that is coming in as 2 bytes. Right? So a good example is, let's say that we want to store 5689 in memory location, and we have to store it at this location. So how do we do it? So for, of course, this I've written it, it's in decimal. Now, of course, it's understood that if we convert this number to binary, then we'll see that it contains about 16 bits of information. And this 16 bits of data is actually 2 bytes of data. So if you can see this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if this is in decimal converted to binary, there are about 16 bits of information, and it's 2 bytes, and we have to store at one location, but the cell size is 1 byte. So we have the 1639 bytes. So how does the computer, or how does the memory location, how do we store, how is it wired to store such kind of information? Does it go ahead and reject and say, look, you can't store 16 bit of information or 2 bytes of information? I'm only cell size, my cell size is 1 byte. No, but there's a way, right? Now guys, I just want to make you understand that this, if you divide this number, this number that we have right here, which is in binary form, if we divide it, we can actually divide it into hex as this. There's 1639, and 16 would actually represent the upper byte, and 39 could actually represent the lower byte. Now upper byte, how do I know that this is the lower byte and this is the upper byte? Well, by upper byte, lower byte, upper byte, upper byte, lower byte, what we simply means is that the byte that is to the left, or the number that is to the left, to the right, belongs to the lower byte, and the number that is to the left in this case will actually refer to the upper byte. Now what we mean by the upper byte is that now there are 2 ways in which this address could hold these numbers in hexadecimal. The first way to do it is to where we start with the upper byte number, and then we get the other number, which is 39, is going to be stored in the consecutive memory location. So because now we are supposed to store this number on this location, but it appears that this cell is not big enough to store a 16-bit long number. So what the memory decides to do is that it will store these numbers in the consecutive locations. Now what are the consecutive locations? So the first location is this location. The consecutive location is that location. So what will happen is that it will get the upper number, which is 16, and store it there, and the lower number to be that. And so much so that we can say this belongs to the upper byte. Right, the byte that is to the left. So we can even count 1, 2, 3, 4, 5, 6, 7, 8. That could be where the upper byte is, and from here we have 1, 2, 3, 4, 5, 6. This could be also the lower byte, right? So now we start with the upper byte, we load it, and we go to the lower byte, we also try to load it. Now there's a methodology and there's a reason, there's a theory behind this, which I just want you guys to really take note as we try to teach you how to work with our memory right here. So for example, now real quickly, I just want to show you in my next slide. So that's how you store that number, right? Now, storing the 2 bytes by first entering the most significant byte. Now, in this case, we said that the most significant byte is the number that is to the left, and the number that is to the right is the least significant byte. So the most significant byte in this case is being 16 as the most significant byte, and this least significant byte is the least significant, 39. And this methodology follows a policy. It's called the Big Indian and the Little Indian policy. In the Big Indian policy, it's where the most significant byte is stored first, followed by the least significant byte, and this is the Big Indian policy. Storing 2 bytes by first entering the least significant. Sometimes we may start with 39 and then end with the what? 16. So in other words, this could go to 0 times 0, 1, and this could go to 0 times 0, 2. All right. At first, we had this one going to 0 times 0, 1, and this going to 0 times 0, 2. All right. So now we can start with this one going to there and then going there, and this is called the Little Indian policy. So, but then it's very much important for us to understand that data is stored in consecutive memory locations, e.g. at 001, and then stored in 2 bytes. That's how you store in a memory size cell size of 8-bit or 1 byte, you are able to store you are storing the 8 bits of information in different memory, in consecutive memory locations. So how do you store a string? I'll leave it that, guys. I want you to go and check how we store a string in memory locations, and that's your homework. All right. So now, in this introduction, we're going to try to look at the AVR memory architecture. Now, we're beginning to go into the reason for our lessons, and having given you the overviews of what we've been looking at. Wait. So now I'm beginning to look at the AVR memory architecture. Wait, just give me 3 minutes. We're beginning to look at the memory architecture layout, in which now we are trying to teach you guys how the memory architecture of the Atmega 32. Now remember, we've said that the Atmega 32 is the chip of choice. We did talk about in the last class that this chip, we're going to use it for learning the basics of assembly language, and that will be our chip. And we've learned the general principles of microcontrollers and microprocessors, and how there's memory in all of this in general. We've referred to that, but now we begin to now target a particular architecture like the Atmega 32. That's the one that we're going to target, and let's try to see how is memory also organized in this chip, for example. Right. Now, the Atmega 32 has got what we call the flash memory. Now, I mention this now because now we're pinpointing. We have what we call the flash memory. The flash memory is basically the... Now guys, I'm getting a bit of some echo feedback from my children right here. I would like to see if we can end right here, and then when I have some good quiet time, I'll begin to talk about this. All right? So that you are able to see, but maybe I can just quickly go through this, and then I'll go through the rest of the stuff when we try to, and then we can talk about some other stuff here. So what's the flash memory? Now the flash memory, this is the memory where you store code. Now if you look at the Atmega 32, just like most of these other microcontrollers, we've got a place where we store code, and we've got a place where we store data. Just simple as that. The place where we store data becomes also a particular memory, and this place where we store instructions becomes also another place. Apparently, the place where we store code in the Atmega 32 is called the flash memory, right? And I want to mention that this 32 right here that you see, it is referred to the size of that program memory, right? In this case, this program memory is 32 kilobyte of space. Is 32 kilobyte of space. That is the size it holds. Now think of this 32 kilobyte as this whole chunk that is the 2 kilobyte in size, and then it has got these cells right here, and such that if you come to think of this 2 kilobyte of space, you just want to think of, all right, so in terms of bytes, what is this 32 kilobyte in terms of bytes? So if think of this 32 kilobyte of size as being divided into cells, and each cell will have a particular address. It will have a particular address. The first address is address number 0, and it has to be placed in hexadecimal. Now, apparently in hexadecimal, in at Mega 32 microcontroller, the address number 0 is given as 00 with 40 digits, and this is the dollar symbol that we get, but then this number is the hexadecimal number. Right. Now, what could be the last possible if you were to divide this 2 kilobytes into the cell locations? The question that comes that how many cell locations and how can you go about the address mapping so that you are able to reach the last cell, and what is the last cell location? That's the one that we need to discuss maybe a little bit before I go into the details. You can see here, for example, that the cell location, the first cell location will be given 00, and the last cell location is actually going to be given as decimal 3FF. Right? Now this shows you that this is really the last cell location. Right? Now there's just one secret, guys, that I need you to understand, and you need to be very, very, very much careful on this one. If we say that it has got the 2 kilobyte of space, right? How is the cell? What is the first thing we need to address ourselves is that, well, what is the cell size? Because the number of cells times the cell size gives us the memory size of that. So apparently when we talk about this flash memory, it is weight addressable. Each cell is 2 bytes long. That's how big each cell is. It's 2 bytes long. Alright? So each cell is packaged as 2 bytes, 2 bytes, 2 bytes. Now if it is packaged as 2 bytes, the other thing that we want to really take note of is to see, alright, so let's say for example I've got the 2 kilobyte of space, right? So the 2 kilobyte is nothing but 32. How many bytes are this? It will be 32 times, because we know that 1 kilobyte is equal to 1024 bytes. And so if we multiply 32 times 1024, what we get? We're going to get what? We're going to get 32,768, if my memory serves me right. Okay, so I'd like you to verify what is the 2 times 1024. I don't have a calculator with me. I just want to, maybe let's see if we have that. Let's just try to escape a little bit out of this. Okay, so I'm getting a bit of some feedback. So what is 32 here? So let's try to get, because you need to understand how these memory locations, how did we come to 3FF as the last cell location? Well, the first cell location is understood, it's all 0000s, right? But now we need to look at what is the last cell location and what is its size and how did we come to 3FF in this cell location? Because it's the 32 kilobyte of space. So what we need to do is perhaps to try to go to the is to try to see if we can go to the calculator. I'd like to get my calculator and then try to see if we can get it. just try to look at the size, memory location. Once we get it, I'm just analyzing. Let's try to discuss.
You drink some tea.
Don't come and disturb me. Go. Okay, babe. Let me go and write. Okay. So now, what I'll do is I'll try to walk out of this and then try to say come back and let's see if we can have we can do a bit of some calculations. So I'd like to get my calculator. What's happening to this computer? So slow. Okay, so now let's see what we have. All right, so what is the discussion? The discussion is that what is the last possible cell unit? So the first possible cell unit is that it is we are having let's just remove all of this so that we don't get disturbed. So unit 0 is the FF. That's the question that we need to address right now. How did we arrive at the 3FF? How did we arrive there? Right? That's the point. Now, guys, if we get to our calculator, we can try to see if we can change. Just a minute. Just get the things in place. Okay, so now here it is. So I'm gonna change this calculator maybe to something like standard. Or in fact, even here I can work with it. Or maybe let's just get a standard for now. So what I want to do is that I want to say 32 times 1024. Now 32 times 1024 gives us, yeah, oh my goodness, messed up. So 32 times 1024, 1024, this gives us the 2,768. Now, if you look at the 2,768, what is it exactly that we are actually working with right here, so that all of us have an understanding of what's going on? Because now the determination here is to get the cell size, the size of the last cell, or the location address, the memory mapping of the last cell. How did we get there? Why is it at 3FF? Now, this is the point that I'm trying to prove right here. So we have the 2,768. Now, if you check right here, don't come here, don't come here. You're disturbing me. So now what we can see here, right? I would like to let me just go to the board here, right here, to just try to help us understand this, because this is important. So suppose now that we know that our file location is basically like right here, like this. So we say that the first cell location, no big deal, it's cell number 0. And it will have 4 orders, and now we saw that the last one was 3FFFF, right? That's what we saw. So it means that if this is 0000, then the next one, of course, is going to be 0001, 002, until we reach the last. So now the question is, how did we arrive here? Why? How did we get this? This is exactly what I was trying to say. And then this one is 32 kilobyte of flash. It's 32 kilobyte of space. And then each cell is 2 bytes. 2 bytes. That's how each cell is packaged. So if we want to get how many bytes, because we say that the memory is measured in bytes, so we can say 32 times 1024, and we got that one as 32,768, right? Now, since the packaging of the cells is in 2 bytes, and then we have 32,768 bytes, then we could actually divide this by 2 to know how many packages of these are going to be, because we package 2 bytes, 2 bytes, 2 bytes. Now if we package 2 bytes, 2 bytes, of course we're going to have 1, 6, right? Then we're going to have 3, right? Then we're going to have what? We're going to have 8, 8, 4, right? Now that's it. So we're going to say that now we have got 384 2 bytes, because now there's this 2 byte, 2 byte, 2 byte, and in total there are actually about 16,384. Now if there are 16,384 of these 2 bytes packaged like that, the first one starts from 0, which will be the first one, but then the last one we will be, now if we start from 0 and it's 16,384, then the last one should be 16,383, right? This is the decimal equivalent. Now if I come now to the calculator, let's see if this decimal equivalent actually is that number, that there, right? Because that's what it is, because the packaging is done in 2 bytes, 2 bytes, 2 bytes, right? So now I have to divide the 2,768 to give you 16,384, but then if I have to map this memory size starting from 0, the last one will be 16,383. All right, now if we can do this, now come back to the calculator and let's see what happens. Let's go to the programmer, right? Programmer right there, and now we're saying 16,383, right? Is that what we got? So we have a number in decimal, which is 16,383. Right, now you can see here, right? That's what we get. You can see here, right here, if you take notice of this, that's exactly how we managed to get the last hexadecimal to that value right here, because that is the last cell location. The last cell location is 16,383, but this is expressed in decimal. So the hexadecimal equivalent of this number is actually 3 triple Fs, and that's how we get it. Now I did mention, guys, that the memory locations are actually chopped. The flash memory, which is the memory that is used to do the programming within the microcontroller at Megathek 2, is actually chopped in from 000, and the last one is the 3 triple Fs, and this is the one I just proved to you that yes, it's true, it has got the 2 kilobyte of memory, but then the data is organized as 16k 2-byte words. And I hope you understand this, because program instructions are either 2 or 4 bytes long, because program instructions, they can either be 2 or 4 byte long. So therefore the memory instructions are organized as 2 bytes. Now each word, now if you can see here, actually you can see here that between this point and that memory location we have got, this is a special location. It is reserved for the recept and interrupt vector section. Now guys, I'm not going to go into details about the reset and the vector interruptions, but then we're going to have a detailed discussions on interruptions as well. But right now, just suffice to say right now that anything that is between this value and that value in terms of the addresses, all the addresses that are lying in this range, they are reserved for that. And from here to somewhere here, you can see this is where your application section, this is where your program goes. Your program goes into these sections right here. And the last section also is going to be reserved for what we call the boot flash sections. And again, I'm not going to talk about the boot flash section. I will have maybe some discussion also on the boot. But right now, this is how your memory is actually organized. You just need to understand that between this and this is the where your program goes, and that is this a special location for that, and that's also a special location for that. Now we can see that a memory has a unique address beginning with this and ending with that. Now some flash memory is reserved or protected, like this one where for two reserved and the last, they are also protected. You don't have access to them because they are actually reserved by the manufacturer for the purpose of doing those same functionalities that are just being shown. All right, so that's how the flash memory is actually organized, and we need to just take note of that when we talk about that Mega32. And what is the flash memory used for? Well, the flash memory is actually used for storing data, for storing the code, for writing the program. Right now guys, let me just end right here because the video is going to be too lengthy. But then now in the next class I'm gonna show you also the program, because since we've said that this is where we do the coding, this is where we write our code goes right here, right? But then now we have a location where we also do the data, where we do the data in the Mega32, right? Now what are these things, right? Where do we store the data? Where do we store the data? Data is actually stored in the memory such as the SRAM, the EEPROM, and I'll talk about them in detail, because memories could be read-only memory. There are those which they're volatile memory, and those that are non-volatile. But right now, just suffice to say that it's a flash. It's found in that Mega32, and it's used for writing the code, and it's the 2 kilobyte. And this is how the address mapping goes. All right, and I'd like to thank you for viewing. I'll see you in the next class.